to the desired form, 6ijk nj nk over r cubed, when I am at radii small compared to a reduced wavelength. So it's pretty straightforward mathematics. But the one clever thing, and the only really clever thing here, is to know how to write down a outgoing wave solution of the wave equation. To get rid of the indices by differentiating twice. And then to basically be guaranteed, if you've thought through what you're doing, that this has got to be some multiple of the desired quadrupolar term in the near zone, and to discover that the factor 2 is what you need here. Okay. So any questions on that? So we now have a form that is valid for the gravitational, for h bar 0, 0 throughout the local wave zone and the weak field near zone. We now need to get expressions for the other, for h bar 0j and h bar jk. So if this is the form of h bar 0, 0, and we need to have it be true that h bar 0, 0, with I take one time derivative, needs to be equal to minus h bar 0j comma j. That's the Lorentz gauge condition. This enables me to compute h bar 0j, just using this Lorentz gauge condition. And you can just read the answer off of here. And the answer is then that h bar 0j that I need, there's going to be a sign flip. It's minus 2 times 1 over r ijk of t minus r, with only one time derivative, one divergence on it. To repeat it again, if I take this expression and I take a divergence on the j index, and I take that expression and take a time derivative, I have the same thing aside from a sign. And so this is the form that h bar 0j must take. So I infer from the Lorentz gauge condition, I infer from knowing what h bar 0, 0 is, I infer what h bar 0j must be. And then I can go one more step, h bar jk, comma, h bar jk, comma k must be equal to minus h bar 0j, or j0, comma 0, which is the same thing as minus h bar 0j, comma 0, since h bar is symmetric. I know this guy, I just put one time derivative onto that. And so I ask myself, what do I need for the space-space piece? Then when I take its divergence, I get the same answer, and it's pretty obvious that h bar jk is just going to be equal to plus 2, 1 over r ijk of t minus r. So to reiterate, if I take a k derivative on here and flip a sign, I get the same thing as taking a time derivative on there. And so I've used the Lorentz gauge condition twice to move from the time-time to the time-space to the space-space part of the trace reverse metric perturbation. And I'm there. Now all I want to do is I go out into the local wave zone and I take the transverse traceless part. And so the bottom line is that in the local wave zone, hjk tt, I get just by projecting out the trace on this guy, and it's equal to 2 over r ijk at location t minus r, the retarded location, transverse traceless piece projected out. Now, this way of deriving the same formula is I think I had you, well, as I talked about last time, and I've forgotten whether I had you actually derive this on the problem set or not. So you derived it on the problem set. This way actually is a much more powerful way, because this way of doing it makes this formula automatically be valid when the source has strong internal gravity. If the source has strong internal gravity, we don't know how to express the mass quadrupole moment as a integral over the source. Our expression for the mass quadrupole moment is an integral over the source, this expression here. That's valid only in the slow motion weak gravity limit, in the Newtonian limit. However, if you have a strong field source, such as a spinning neutron star, where Newtonian theory is not valid in the interior, and where this expression is not valid, you can still go into the weak field near zone and look at the form of h bar 0, in there. You can look at the gravitational field in the weak field near zone, and you can just ask, what is the mass quadrupole moment? And you leave it to somebody else to figure out how that mass quadrupole moment can be written as some sort of integral over the source, since you don't yet know enough about nonlinear gravity to know how to do that. But if you just actually go into this region where Newtonian theory is highly valid, it's not valid in the source, but it's valid in here, you can just use measurements like any Newtonian physicist would to measure the mass quadrupole moment. You just measure how the gravitational attraction changes as you go around, and read off a mass quadrupole moment from the angular dependence of the gravitational attraction. Or somebody does the calculation for the interior and tells you what the mass quadrupole moment is in here. But once you know the mass quadrupole moment in here, it appears in h bar 0 in that form, and it is guaranteed by just the mathematics of linearized theory being valid over those two zones. It's guaranteed that the gravitational wave field will be 2 over r times the transverse traceless part of ijk. Okay, any questions about that? Okay. This is one piece of a very general calculation. You can do this analysis for the full multipolar decomposition of the gravitational field in the local wave zone and weak field near zone. So instead of just writing down the mass quadrupolar piece, you can write down the full sum over both families of multipole moments, and you can write it down in a form that is a straightforward generalization of this expression here for each of the multiple moments. And you can then go through the same process as I did here to infer what is the gravitational wave field and how does it connect to the field in the near zone. And I'll give you some reading on this. And what I want to do with regard to the higher order moments is I just want to make some remarks about the current quadrupole moment. It's the other term will turn out to be important, very important, in one source of gravitational waves, oscillating neutron stars. There are certain modes of oscillating neutron stars called R modes, in which the radiation is predominantly current quadrupolar. So I just want to tell you what this current quadrupole moment is. So if you go through the same analysis as I have been going through, but work now on the h bar 0j piece of the metric. So we want to work with the equation that says that del squared h bar 0j is momentum density. And we want to make sure that the solution that we get to it has vanishing divergence. You can apply this same technique of writing down a solution of rho Vj in this case over x minus x prime. Expand the 1 over x minus x prime out and just grind away and then do some integrations by parts. And you can wind up in the end with the following expression for the time-space part of the metric in the weak field near zone. You wind up with an expression that says that that h bar 0j is equal to minus 4 n cross s over r squared, where s is the angular momentum. So it's the integral of the radial vector inside the source crossed into rho at x prime, v at x prime, d3x prime. So it's just the standard angular momentum. And that's the current dipole moment is this angular momentum, and you get a minus 4 n cross s. So there's been some algebra, of cross products used in order to get to here. I'm just telling you the final answer, which you could derive for yourself. I might not give it to you as a problem set. It's a little bit of messy algebra. It depends on how I feel tonight after supper, whether I decide to give it to you as on the problem set or not. Okay. And the next term can be written as minus 4 over r cubed. So this is a dipole term, so it's 1 over r squared. 4 over r cubed, I'm going to write it as n cross s dot n. This is a notation I've not used before, but I'm using this notation because I don't want to get into the mathematics of something called the Levi-Civita tensor, which most of you may know, but I don't want to get into it. So S has two indices. I'm taking a cross product of the unit radial vector on the first index and a dot product of the unit radial vector on the second index.
Can you write it down in terms of Levi-Civita tensor?
Okay, so for those who are accustomed to that Levi-Civita tensor, that would be epsilon A, B, C, N, A, S, just a second, epsilon J, there's one free index, that's this J, J, A, B, N, A, S, B, C, and C. So this is a cross product on the B index of S. That's a dot product on the C index of S. So those are the first two terms in a power series expansion that you can generate, just grind out by the same technique as I did over there, and by doing some manipulations of cross products and maybe some integrations by parts. I've forgotten what all's involved, and I haven't done this calculation since about 1978. So, okay. You then write down a solution to the wavy, well, you then know this can't produce radiation, so you focus on that term. Oh, and you also obtain, since I began with an expression assuming a source, rho Vj, you obtain an expression for Sjk, and I just want to tell you what that is. Let me write it. SBC is an integral of the angular momentum density, the B component, and then times xc d3x. And so it's the first moment of the angular momentum distribution. This is angular momentum density. You take one moment, you multiply by one factor of x. You now have a second-rank tensor, and then you have to symmetrize. Let me just use an S for symmetrize. I have to symmetrize on the two free indices. So you take 1/2 of this with B first and C second, plus 1/2 with C first and B second. So you symmetrize on that. So in fact, the analog of the magnetic quadrupole moment is, and then you have to remove the trace too, okay? So you take the symmetric, you symmetrize it and remove the trace. So STF means remove the trace, S means symmetrize. So it's the first moment of the angular momentum density, symmetrized and with the trace removed, is what this current quadrupole moment is. And then you can go through the same process as I went through of over here of writing down an outgoing wave field as a solution to the wave equation. Oh, you have to do one other thing. You have to verify that this has vanishing divergence, and you can verify it that it has vanishing divergence. Then you build yourself a outgoing wave solution or solution to the wave equation for h bar 0j that reduces to this in the near zone, and then you bootstrap yourself over to h bar jk using the Lorentz gauge condition, the same set of processes as I did before, and you wind up then in the end taking the transverse traceless piece with hjk transverse traceless is minus 8/3 1 over r n cross s t minus r, the jk component, transverse traceless. So on the first slot, or the first index of S, you take a cross product. So, but this has two indices, so there are two indices in the end at jk. Or in terms of, with the Levi-Civita tensor present, there's 1 over r epsilon j a b n a s b k of t minus r, symmetric transverse traceless. Symmetrize on j and k and take the transverse traceless part. And the same pattern works for all the other moments. So I've just told you what you get. But having told you what you get, I want to also notice the magnitudes, the relative magnitudes of these terms. So let's look at this term, that gravitational wave field for the current quadrupole moment, and this gravitational wave field for the mass quadrupole moment, and see how big they are. So I need two time derivatives on here. What happened to my time derivatives all the way through here? Damn. So let's just go back here. H bar 0, 0 had no time derivatives, but in order to satisfy the Lorentz gauge condition, I need one time derivative on there. And when I come down here, I need two time derivatives on there. So that basically I've exchanged two factors of 1 over r for two time derivatives. Okay. I'm surprised somebody didn't jump all over my back for that. And similarly over here, I need to exchange two factors of 1 over r for two time derivatives, and so I've got two time derivatives on here. Okay, now in order of magnitude, this gravitational wave field here, the mass quadrupole moment looks like the mass of the source times its size squared. I have two time derivatives on it, so it's divided by lambda bar squared. Lambda bar is basically an angular frequency of the internal motion, so this looks like and 1 over r. And so this looks like mv squared over r. So it's the Newtonian gravitational potential produced by the internal kinetic energy of the source, which is something that I said in my introductory lectures. Over here, the current quadrupole moment is a density that's integrated over space, so that gives us an m. There are two x's, so there's an L squared, and there's a v. That's the magnitude of the current quadrupole moment. Down here it appears with two time derivatives, so we've got m L squared v over lambda bar squared, and then a 1 over r. And L squared over lambda bar squared, again, is the internal velocity squared, so that's m v squared over r times v. So this term is smaller by one factor of internal velocity than the mass quadrupole term. The same thing happens in electromagnetic theory. At any order, the magnetic dipole term is down by a factor of v from the current, from the electric dipole term. The magnetic quadrupole is down by one factor of internal velocity if its charge is moving around from the electric quadrupole term and so forth. So the current terms are down by one factor of v over c, internal velocity divided by the speed of light, from the mass quadrupole terms. But in those cases, as is the case with R-mode oscillations of neutron stars that Lee Lindblom will talk about, in those cases where there's not much mass change, so the mass quadrupole moment is not very dynamical, there can still be a lot of sloshing of the material, and so you can have a big oscillating current quadrupole moment, but a very small oscillating mass quadrupole moment. And in those cases, the current quadrupole dominates.
What's the name of this thing again? This is the...
So this is called current quadrupole. That's one phrase. This is the phrase typically used. It's the current quadrupole moment. But what it is actually a moment of the angular momentum distribution. But that's also, in some sense, a moment of the linear momentum distribution. And linear momentum is the same thing as mass current, and that's where the phrase current comes from. Just as the electric current is the thing that generates the magnetic moments in electromagnetic theory, so the mass current generates the current moments in general relativity. And in electromagnetic theory, the electric current is the source of the oscillating magnetic moments. In gravitational theory, the mass current is the source of the oscillating current moments. Okay. Yeah, questions? Okay, in the last 15 minutes, I want to turn to the issue of the energy loss and angular momentum loss from a slow motion source. You've already analyzed one slow motion source in the homework. You've done the problem of two stars going around each other, a binary star system. You computed in that analysis, you computed the gravitational wave field, but you did not look at the question of how much energy does it carry away from its source. And that's what I want to talk about now, because that's something that Sturl is going to need when he talks about sources next week. So the rate of loss of energy from a source is pretty obviously should be computable by just doing an integral of the energy flux out here in the local wave zone. So I go out into the local wave zone, I build myself a sphere of radius r out in the local wave zone. And I look at the radial component of the gravitational wave energy flux, and I just integrate it over the sphere. So dE dt is going to be minus, because you're losing energy, the integral of T0r gravitational wave d surface area over the green sphere. And T0r gravitational wave is 1 over 32 pi times hjk transverse traceless, comma 0, hjk transverse traceless, comma r. And the surface area is r squared d solid angle. D solid angle being, of course, sine theta, d theta, d phi. And for the hjk transverse traceless, I want to go in and put in this expression in terms of the mass quadrupole moment. So I take my standard mass quadrupole moment expression. That's then 2 over r ijk, two time derivatives at t minus r, transverse traceless. It's what I put in there. Now, the dependence on theta and phi is carried by the unit radial vectors, and the unit radial vectors are present here, though they appear to be hidden. They're present in the transverse traceless projection. You've got to get rid of the radial piece and then remove a trace. So let me write that down explicitly. That's 2 over r I j k double dot. Let me write that as I a b double dot. I'll write it as delta a j minus n a n j delta bk minus nb nk. That gets rid of the radial part, because this thing, for the radial piece, if I point in the r direction, this is the Kronecker delta is 1 in the r direction, and these guys are 1 in the r direction if I'm using a spherical polar coordinates. And so this projects out, gets rid of the radial piece, keeps only the tangential piece. In a spherical orthonormal basis, this will just project out the transverse piece. And then I have to remove the trace, and I can remove the trace, it turns out, by then subtracting off a delta AB minus NA NB, then delta JK minus NJ NK, and a 1/3. So I'm just telling you, asserting that this is a way formally to pull out the transverse traceless piece, just formally. But then you know that if I'm working in spherical polar coordinates, well, if I go back to Cartesian coordinates, these are functions still of theta and phi. The z component is cosine theta. The x component is sine theta, cos phi, and so forth with the inner radial vector. So that's where the dependence on theta and phi comes. And so this formal expression, when I talk about it in this language, it has a rather complicated theta phi dependence. But I can put that in there, and I can just do the integral over theta and phi. I'll give you some reading where the tricks for doing this in terms of staying strictly in Cartesian coordinates are spelled out. But the bottom line after you do this computation is a very simple bottom line, that the energy loss rate is equal to minus 1/5 ijk 3 time derivatives on it, ijk 3 time derivatives on it, and let's average over a few oscillation periods. So the bottom line is it's just 1/5 the square of the third time derivative of the mass quadrupole moment. And there's an analogous expression that you can get by analogous techniques for the rate of loss of angular momentum from the source. Just again do a integral over of appropriate quantity over the sphere. The rate of loss of angular momentum is minus 2/5. Let me write this with a Levi-Civita tensor. We're not probably going to use this, but I'll talk about the Levi-Civita tensor briefly. So you're asked to take this takes a cross product on the A and B indices to produce something that points in the J direction. The A index is here and B is there, so it's a cross product between the first two indices of these I's, and then a dot product on the second two indices. That's what it is. And the first I has only 2 time derivatives, and the second I has 3 time derivatives. So it's an expression that you can work with, you can actually do practical calculations with, and it's obtained by the same kind of a surface integral. And then you can work out similarly expressions for the contributions of the current quadrupole moment to the emitted energy and angular momentum. And as you would expect, the current quadrupole moment contributions are typically smaller than the mass quadrupole moment. Smaller by a factor of V over C coming from this, the first term here, and V over C from the second, but smaller by 2 factors of V over C, where V is the internal velocity. So the current quadrupole, except in cases like our modes of oscillation of a neutron star, where the mass quadrupole is suppressed by the nature of the motions, the current quadrupole is unimportant, and all the other higher multipoles are unimportant. You can also work out the rate of loss of, or rate of change of linear momentum, which just corresponds to the source being given a kick by emission of gravitational wave momentum. And linear momentum loss turns out to arise from a beating of the mass quadrupole against the current quadrupole, and also a beating of mass quadrupole against mass octopole. So it's a beating of different kinds of moments against each other. And that's kind of hard to do, and so the kicks that are given to sources typically by gravitational wave emission are not terribly big kicks. But you can work them out in full detail, work out expressions for them by the same techniques as I have been talking about. So the last thing I want to do is just tell you what happens when you apply this to the binary system that you worked on in the problem set. And I'm going to give you an exercise to do computations of this on the problem set, because Stirl will use this. So if you do a computation with these formulas for a binary with mass m1 and m2, reduced mass is m1, m2 over the total mass. The total mass is m1 plus m2. So in the problem set, I had you write the final answer in terms of reduced mass and total mass, even though you treated an equal mass binary. I just asserted that that formula was valid for unequal mass binaries. And if you go through and just compute this energy loss, you wind up then, in this case, with dE dt is equal to minus 32 fifths mu squared m cubed over a to the fifth, where a is the separation between the two bodies. I remind you that the angular velocity is equal to m over a cubed square root by Kepler's law. And so you can also write this in terms of the angular velocity instead of in terms of a, that is in terms of the masses and the angular velocity. Since the total energy is just mu m over 2a, that is the gravitational, or mu m over a, the gravitational potential energy is the negative of this. The kinetic energy is twice this, and so the total energy is this. That means that the time derivative of the total energy is given by that expression, so it is minus mu m over a squared dA dt. So this becomes a differential equation for the separation between the two stars as a function of time. And you can easily solve the differential equation, since it's just a 1 over a to the fifth on the left-hand side. And that tells you that a is equal to some initial separation times 1 minus t over tau naught to the 1/4 power. So at t equals 0, a is equal to the initial separation. And when time tau naught has elapsed, the two stars have come crashing together. So they're spiraling together to smaller and smaller radii and finally merge. And tau naught then works out to be 5 over 256 a naught to the fourth over mu m squared, or 5 over 256 m squared over mu times m omega to the 8/3. And I write it in this way because twice omega is the angular frequency of the gravitational wave, so that's an observable. So this time and the time until the two stars come crashing together depends on the masses and on the frequency of the gravitational waves, which you can measure. So the frequency of the gravitational waves is 2 times omega over 2 pi, or it's omega over pi. So I can rewrite this time until they come crashing together in terms of the gravitational wave frequency. And this is the last thing I want to do, just give you some numbers. So in the case, so you wind up using some numbers relevant for LIGO, you get about 3.04 seconds divided by the gravitational wave frequency in units of 100 hertz. 100 hertz to the 8/3 power. 100 hertz is the frequency at which LIGO has its best sensitivity, times the mass of the sun over what we call the chirp mass to the 5/3 power, where the chirp mass is mu to the 3/5, m to the 2/5. And it turns out that all the properties of the in-spiral in this mass quadrupole moment approximation are determined by the chirp mass. The chirp mass governs the rate at which the stars spiral together. And it's just the chirp mass that's appearing in this expression if you do a little bit of algebra for the time until merger. What this says is in LIGO you typically deal with neutron stars and black holes that have masses of order of the mass of the sun or a few times the mass of the sun. So at 100 hertz you have of order 3 seconds left. And at 10 hertz, which is when the signals sweep into your frequency band, you've got something like 24 minutes. Because it's a very steep power, 8/3 power of the frequency. So a few tens of minutes from when the waves sweep into the LIGO frequency band, a few seconds from when they reach the optimal frequency, optimal sensitivity until the end. And so that's the story in LIGO. By comparison, for LISA, if you put in masses appropriate for LISA, which are thousands to millions of solar masses, and a frequency appropriate for LISA, which would be, say, 1/100th of a hertz, a period of 100 seconds, you wind up with numbers of a few days. And so if you go down to, say, 3/1000th of a hertz, you've got times of the order of a year. And so for LISA, in the LISA frequency band, your signals last for days to years. But for LIGO, they last seconds to minutes. Okay, that's cool.